one just show in terms how this translates into in terms of irregularities, behavior, and effect on GNSS. We are going to concentrate on GNSS for this talk. So first of all, I like to take what Tobias told you yesterday and extend a little bit, just to tell you that GNSS are excellent, provide an excellent probing of the ionosphere. Actually can rely on several constellations. The global one are GPS, GLONASS, the Russian one, the European one, Galileo, and Beidou. And the good thing is that they cross entirely the ionosphere, providing probing all the layers. Of course, we don't resolve the altitude. So typically what we deal with GNSS, we are able to reconstruct the GNSS is a kind of squeezing of the ionosphere on a layer. Usually it's 350 kilometers, but it varies a lot as the actual layer of the ionosphere. It's not a layer, of course. And most of all, it is the ionosphere is the most poses the most dramatic threats to GNSS, particularly in the error budget. It presents the largest one. So what we can, when we deal with GNSS, what we can actually measure? We can measure the phase and the code of the signal, which are that have many terms inside. The I term is the ionospheric term. And you see here all the various components of the error budget. So the presence of a smooth ionosphere introduces a delay of the modulation, so the code measurement will be larger than in vacuum, and advance of the carrier phase. So the carrier phase measurement will be smaller than in vacuum. But mostly you can get these two quantities to do a lot of things. Usually we use combination of GNSS measurements. This one is the ionosphere free linear combination. We deal just with multi-frequency because observation, so because GNSS satellites emit several frequencies, at least 2 or 3, and by combining the frequency in the so-called ionosphere-free linear combination, this is the frequency of the first frequency, this is the phase of the first frequency, and then the relative of the second one. It removes up to the 90.9% of the ionospheric effect, and which depends on the inverse square of the frequency, and it's mostly used for positioning and to assess the higher order ionospheric effect, which are below the centimeter level under quiet conditions. And usually we use also the geometry-free combination, which is actually just the difference between the phases of the two. It cancels the geometrical part of the measurement, and it's used for the estimation of the total electron content, which is one of the parameters you have seen in these days. So it is defined as the integral of the plasma density along the ray path connecting the receiver to the satellite. That's the expression of the slant tech you can get from the observable of the GNSS. From the GNSS observable, there is this epsilon, which is actually not an epsilon, is the error contributing to the determination of the slant TC, which is actually also the career of many researchers. Some of them are also here, and it's usually measured. It's not a trivial problem. It's not the subject of this talk, but really it is a big trouble. Probably only God knows the real TC. So it is expressed usually in TC unit. As mentioned, we can also map this slant TC into a vertical TC to get rid of the geometry, but we must put onto the table some assumptions. So for instance, that you have to put this information on a specific Pierce point, again 350 kilometers is the standard assumption, and you can get a vertical TC. And you can even use the TC to make a time derivative. I already introduced something like that yesterday, to obtain the so-called rate of TC change, which is quite often used to investigate fluctuations of TC. This is, for instance, a day of observation from one receiver in Antarctica, and each color represents a satellite, so you may see that somehow the TC is a largely varying quantity. So, bear this in mind, and let's start talking to ionospheric scintillation. So the word scintillation is not something invented for the ionosphere. There are actually three big categories of scintillation. There is the interplanetary scintillation, the tropospheric scintillation, the ionospheric scintillation. Each of them has a cause. The interplanetary scintillation is due to inhomogeneities in the solar wind. The tropospheric one is due to the neutral turbulence, and the ionospheric scintillation is due to ionospheric irregularities. And what they cause? They cause fluctuation in the intensity of radio stars, fluctuation of the optical ray path, the twinkling of stars, and the fluctuation of the amplitude and phase of the signal recorded by GNSS satellites. So if we want to concentrate and understand the scintillation, we can use somehow the same it's the same of the twinkling of stars. So to understand the effect, we need to say something about the cause. So before speaking about scintillation, be patient, and let's start again with the ionospheric irregularities. So I just stolen this slide from Ivan's talk. It's yours, you know. So what are irregularities? Thank you. They are anomalies. So positive or negative gradients with respect to the background ideal smooth ambient ionosphere, which actually doesn't exist. Is there a quiet ionosphere behaving in a quiet way? I don't know, probably not. So, but we need to think in terms of variations, gradients of density with respect, or passage of gradients of density, spatio-temporal gradients of density that have, as I mentioned yesterday, they vary on a large scale size ranges. So they go from the centimeter level up to the 1,000 kilometer scale. And remember that the scale is not an absolute scale. In this case, I will talk about irregularities from the GNSS perspective. So there are small scales for GNSS, medium scale for GNSS, and large scale for GNSS. Small scale irregularities are the problem for GNSS. I will show you before. They are usually due to the instability process, in particular to the growth and decrease of the instability process that lead to formation of small scale irregularity. There is kind of this magic sentence, few hundreds of meters, which is the order of magnitude of the small scale irregularities below the so-called Fresnel scale. I'm going to tell you more. And they are due mainly to Kelvin-Helmholtz and gradient drift instability at high latitude. They are rare because the scales are rare. The formation of scale is rare because it's due to the forcing from the geospace. While you learn that those embedded in the plasma bubble and created by the Rayleigh-Taylor instabilities are very common. Then there are the medium-scale irregularities. They are usually formed at the boundaries of larger or large-scale irregularities. You will see scales ranging from above the Fresnel scale, so above 300 of meters, above to few tens of kilometers, in the auroral oval, in the polar cap, because of the patches, the auroral broad, the Sauer-Menasse densities, and equatorial plasma bubbles. And they are a problem, not the problem, because they can be somehow treated. The one in the high latitude are mostly storm time phenomena. The one, the equatorial plasma bubble, are modulated, again, prompt penetrating electric field, the disturbance time electric field, and they are modulated by storm time phenomena due to the changes into the electrodynamics of the low latitude ionosphere. And then there is the large-scale structure that are not a problem besides TIDs, but I'm not going not to talk about that. So, ionospheric irregularities are variation of the plasma density. So your signal undergoes through refraction because it passes from different zones that may have different density, so it changes the index, the refractive index changes at the boundary between of the irregularity. It is characterized by the fact that the refraction is covered by the full ionospheric spectrum of irregularities, at least from the large to the small one. It affects only the phase, and the physical mechanism is the phase mixing. So the phase of the satellites, the received signal are mixed at ground. And then that's the problem. The problem is the diffraction, because it affects scales up to the Fresnel scale. I'm going to tell you, don't worry. It affects both amplitude and phase, and the physical mechanism is decorrelation and interference. So what is the Fresnel scale? The Fresnel scale is an elliptical zone in the free space which radio waves travel directly from transmission to reception without significant alteration. So you can determine, if you assume that your ionosphere is a thin layer, an irregular layer, but located in as a thin layer, you may reconstruct with some calculation this Fresnel scale, which is actually the square root of the frequency of the wavelength of your probing signal and the distance from the phase, from the screen, so from the irregularity layer. And if you consider the fact that the wavelength of GPS satellite is about 20 centimeters, and that you can assume in the hover propagation 315 kilometers, the order of magnitude is about a few hundred of meters. If diffraction occurs, if the irregularities has a typical scale size which is below this Fresnel scale. Okay? So in terms of numbers, remember I said this magic sentence, few hundred of meters. So if you consider that there is a varying geometry of observation, because you track your satellite from the rising its rising on the field of view until it disappears, the scale, for instance, may range between 100 and something to 600 and something. And of course, it is not something that affects just GPS, but scintillation affects other frequencies, and it scales with the frequency according to this formula, and you may have from a few hundred of meters up to few tens of kilometers for HF. How to measure scintillation? So, ionospheric irregularities causes fluctuations due to refraction and diffraction on your signal. You need a way to measure. To measure scintillation, we use dedicated receivers. This is the receipt for a scintillation monitor receiver. High sampling frequency, I'm going to show you why. Low noise oscillator, because you want to have very accurate measurements of the phase. A stable clock for the same reason. A firmware able to provide the scintillation indices that I'm going to introduce in real time. And these are the various generations that I use, at least in my institute, have been used since 2003 to characterize this, the scintillation. To monitor scintillation, we use these two indices, the amplitude scintillation index and the phase scintillation index. They are statistical index, usually retrieved every 1 minute, and they monitor the standard deviation of the intensity and phase of the signal. Usually 1 minute is selected because it's a reasonable time to see meaningful changes in the signals due to scintillation. So you need 50 years to have statistically meaningful indices. For instance, in 1 minute you have 3,000 samples. If you sample your signal at every 20 milliseconds, 50 years. And typically what you have is a raw amplitude, and you derive these indices. Increases in the signals, in the index means that there is a scintillation going on. So the simplified picture is that you are monitoring your signal, your raw amplitude, for instance, you provide the indices, the signal is going to pass through an irregularity, so the amplitude starts to fluctuate. The worst case is this, where you have a mixing of scattering, the diffraction going on, and then the satellites are more than one, and the net effect could be the reduced accuracy of positioning and the loss of flock. in the worst cases. So it seems to your receiver that the satellite is not there anymore. This is a typical time profile of scintillation indices. This is again one of the receiver we have in Concordia. This is a modeled auroral oval just to show the location of this receiver, which is well into the polar cap. This is the September 2017 storm. This is the amplitude scintillation index S4. This is the phase scintillation index sigma phi. And you may see that there are similarities and differences. So those indices react to the formation of irregularities in a different way. Usually, if you don't treat your phase scintillation index in the way I'm going to show you, you will have more scintillation, more enhancement of the sigma phi with respect to S4 at high latitude. But some activity well corresponds. So in a few words, you have two indices. One measures the variation in the amplitude, which is affected just by diffraction, and one measures the effect on the phase, which is affected by both diffraction and refraction. So if you study the two indices together, you may learn about the various phenomena that are concurring in your picture. We monitor routinely these indices through receivers. If you browse the Science Center, you will find, for instance, scintillation indices and total electron content among the data collections. And you will be directed to the Electronic Space Weather Upper Atmosphere, which is the data portal maintained by INGV, by my institution, which has a section dedicated to scintillation, and where you can find data from all those receivers located all around the world. You may spot that the distribution of these receivers is not random, but I will show you again more. And you can derive a lot of information, but for sure you can derive things like that. So the time profile of the scintillation indices, this is particular, a plasma bubble occurring in the field of view of San Miguel de Tucumán in northern Argentina, so close to the southern crest of the equatorial anomaly. But why scintillation is a concern? Because impact significantly the tracking. The tracking means the capability of keep the track with a specific satellite. On the left, you can see, for instance, it's the value, the dependence on the probability of loss of lock, of losing the lock with a satellite with respect to S4 and sigma phi for high latitude and low latitude receivers. You will see that you have the probability increases as those indices grow up, and this is also another example. This is for low latitudes separated by the three different constellations. This is the scintillation probability on top and the corresponding probability of cycle slips that are another effect that cause losses of the lock with the satellite, in simple word. So tracking is one issue. So keeping the track with the satellite. Of course, the other issue is the performance of positioning. So GNSS satellites are meant to provide the precise positioning, and they behave badly under scintillation event. This is, for instance, work published by some Norwegian colleagues. This is phase scintillation index, sigma phi. This is ρt, which is relative to the ROT. And this is the corresponding degradation of the error with some geodetic technique to provide precise positioning. So you see that as the phase scintillation index increases, also the error increases. And this is also the case. This is high latitude, this is low latitude. This is positioning errors in the east, north, and up direction. This is Hong Kong, a receiver in Hong Kong. When you don't have scintillation, this is the performance of your positioning. When you have scintillation, things start to get worse. So that's fluctuations is the problem. The real scintillation is just the one due to diffraction, because somehow the refraction induces a deterministic effect on your signal. And you can, for instance, mitigate by using the ionosphere linear combination that I mentioned earlier. Of course, it creates, in any case, troubles to the positioning because it creates cycle slips, losses of lock, noise, phase noise, second order ionospheric effect that are below, that are at the fraction of the centimeter level. The problem of the diffraction is that it's stochastic in nature. And its mitigation is very, very, very challenging. Actually, there is no solution for scintillation. Okay, this is the most tricky part of my talk. So, this is the power spectral density of the amplitude signal, which is somehow you might think at the integral of the power spectral density of the raw amplitude you measure with your GNSS as the S4. So S4 is proportional. The indices are proportional to the integral of this index. And diffraction as a function of frequency, which is also the wave number. So you might think that if the diffraction in this way, there is a breakdown of this spectrum. That is exactly the fact that your Fresnel filtering mechanism is going on. So below the Fresnel scale, above the Fresnel scale, so below the Fresnel frequency, you don't have net effect contributing to your S4. You can identify this breakdown as exactly the Fresnel frequency, and from this you can derive also the velocity of the ionosphere, the irregularities affecting your signal. If you consider refraction is covered all the full spectrum. Again, the sigma phi is the integral of this power spectral density. You remember that sigma phi needs to be the trend because the phase of the signal is affected by Doppler because the satellite moves, so the Doppler changes as the satellite moves. So somehow you have to decide where to put your cutoff frequency to remove the Doppler effect on your signal. This is an issue at high latitude because if you are very far in deciding, if you are not good at deciding your cutoff frequency, for instance, going too far from the Fresnel frequency, you are putting order of magnitude of values into your sigma phi, which are not actually the real problem. So this opening is a recent year, a long debate about what is scintillation. Not every fluctuation is scintillation. For instance, this I will ask you, this is the detrended phase on L1, so the first frequency of GPS. Is this scintillation? What's your answer? I define scintillation as a fluctuation. Is it a fluctuation? Yes. Is it a scintillation? You don't know. But if you check the same thing on the second frequency, it happens the same. What if I take into account the ionosphere free linear combination? It completely vanishes. This is not scintillation. This is phase fluctuation, which has an impact on tracking, which has an impact on the fact on your capability of your receiver, but it's not scintillation. This is deterministic. You can cancel with the ionosphere free linear combination. Is this scintillation? You don't know. You need again to do the ionosphere free linear combination. And there are residual fluctuation here. This is scintillation. So somehow you must decide your cutoff frequency to properly identify the Fresnel frequency into your phase measurement. And this is a couple of papers we published on that about this. If you consider, if you proper treat your phase measurement with an adaptive cutoff frequency, you exactly get the amount of scintillation that S4 is able to provide. So the amount of scintillation on amplitude and phase is the same. The rest is fluctuation due to larger scales. The reason for that is related to the velocity of the irregularities. That magic number, 0.1 Hertz cutoff, which is the standard one, derived from low latitudes. The plasma at low latitude moves at 100 meters per second. At high latitude, you can measure it thanks to the retrieval of the Fresnel frequency. It's way larger. And this makes the use of that standard approach very, very rough. Okay, so it's always like this. You will get sigma, if you want to study scintillation, you will get sigma phi calculated with this cutoff frequency. So please, if you want to do it, be wise in using it. Another proxy for scintillation is the ROTI. ROTI is the standard deviation of ROT on a given time window. This has an historical reason. So typically ROTI is evaluated every 5 minutes. Why every 5 minutes? Because it derives from geodetic receiver. So it was born when there was the need to exploit geodetic receiver for ionospheric monitoring purposes. Geodetic receiver were born for other purposes, so they don't need high sampling frequency. So they provide measurement every 30 seconds, 20 Hertz, 30 seconds. So if you want to have a statistical index, in 5 minutes, you have 10 values, okay? So somehow the ROT is able to provide valuable information about flight fluctuation because the geodetic receivers are really spread all over the world. There are thousands of these receivers that are exploited for these monitoring purposes. But the scale they are able to sample depends on the Nyquist frequency of the ROT sampling. And usually they are about to sample from few to few tenths of kilometer scale. So ROTI is not scintillation. It is very useful because it measures phase fluctuation, but it cannot be easily rescaled to weak scintillation. And this is because you need to know the velocity of the irregularities, which is not an easy information to retrieve. This is probably the most famous picture about scintillation. This has been also presented yesterday by Tobias. In particular, the left one is the signal fading due to the scintillation in this old paper by Basu et al. And this is a frequency of the GNSS scintillation in a more, how to say, outreach style paper by Paul Kintner, who passed away some years ago. So, may you recognize why we located the instrument in those specific places? Because we would like to be very close to where the scintillation, the bulk of the scintillation occurs. Okay, I'm going towards the end of the story. So I introduced the problem, I conceptualized the problem. Let's go to have some results, mostly from the climatological point of view, because the climatology can reveal a lot of features of the scintillation. This is, for instance, we are going at low latitudes, so plasma bubble, 99.9% of scintillation there is due to the small-scale irregularities forming during the Rayleigh-Taylor instability processes after the Pont-Sunset hours. And this is the dependence of scintillation measured by a network of scintillation receivers covering the South American sector for one solar cycle. And you see that the formation of plasma bubble, or the irregularities, of the small-scale irregularities embedded into the plasma bubble, has a strong dependence on the solar cycle. So the more we are in the maximum of the solar cycle, the more frequent is the formation of plasma bubble. Not only, it is also able to depict the double-peaked structure of the sunspot number of the solar cycles. Just to prove again the fact that they are really post-sunset plasma bubble, there is this statistical work. Actually, we didn't publish it in a formal way. This what we use for educational purposes. This is a network of receivers located in Brazil. We concentrate on the data in this box, which is actually, we may recognize here the magnetic equator. This is the -15, -20 band around the equator. So this is nicely into the southern crest of the equatorial anomaly. 2 years of data. This is local time as a function of month. These are the solar terminator. It is particularly the determine the sunset. And this is the occurrence of the S4 amplitude scintillation above 0.25, which is the threshold to define moderate to strong scintillation activity. So irregularities form because of plasma bubble, nicely after the sunset. They tend to maximize between October and April, no scintillation even under maximum solar flux condition. This is solar maximum. And they can also live until the end, at the beginning of the next day. So they can also be post-midnight. Usually pre-midnight are plasma bubble forming in your field of view. Plasma bubble in the post-midnight sector are a bubble drifting in your field of view. So when, now, where? This is exactly the same data set. This is the occurrence in geographic coordinate. This is the -15 isomagnetic contour. Again, this is due to the fact that plasma bubble forms, grow, decay, and the small scale tend to be created when the plasma bubble is, the life of the plasma bubble is quite advanced, and they tend to decay, and the bulk of the scintillation is located along this band here. And this is the case of another network in Southeast Asia. Again, geomagnetic equator, -15, +15 isoclinic lines. Again, this is plasma bubble. Yeah, I'm going to... This is the same network. It's March 2015. March 2015 was characterized by the St. Patrick Day storm. And this is, I have a question for you. This is the local time versus latitude. Again, you can recognize signatures of the northern and southern crest of the equatorial anomaly. I have a question for you. We divided the period in two pieces. The first part was quiet. The second part was badly disturbed. Which one is the quiet and which one is the disturbed? The question is, this is the occurrence of scintillation for quiet time and disturbed time in the same month. But I don't tell you which one is the quiet and which one is the disturbed times. Manuel, please don't suggest. Usually, worse geomagnetic conditions, worse scintillation condition. No, at all. This is quiet days, this is disturbed days, because there is this interplay between PPF and DDF. On the average, there is an inhibition of scintillation. I go fast through the high latitudes. I'm going to show some results we published some years ago about the climatology over more than one solar cycle of data in Svalbard Island. We were very lucky because we installed there in late September 2003 a scintillation receiver, thanks to Giorgiana De Franceschi, who was my boss. Was very wise because the Halloween storm arrived, the November 2003 storm arrived, and we are probably the only one in the world having scintillation data for that storms. So this is, at high latitude we have to change a little bit the way of thinking. So we must think in terms of magnetic local time and magnetic latitude. This is a map of 11 years of data, 12 magnetic local time. Okay. Let's do like this. 12 magnetic local time, 0 magnetic local time, afternoon and morning sector. So in particular, this is sigma phi in the traditional way. So all the scales are there. This is S4, so just small scale. And you see here, for instance, that there is a signature at 12 MLT and a signature in the midnight sector. This is due to the fact that there are precipitating particles in the cusp and in the midnight sector. The black and red lines are the modeled auroral oval. So you will see that this is exactly the signature of the cusp, so the point where do you have the bulk of the precipitation of particle. That creates medium scale irregularities because you don't see it here in the S4. While you see signature in the midnight sector in the S4, this is the fact that you have the tongue of ionization that migrates into the polar cap and tend to fragmentate because of the Kelvin-Harmonic instability or gradient drift instabilities and create small-scale structures. Almost finished, Tobias. This is the dependence on the geomagnetic condition, again, sigma phi in the traditional way, and as for in the traditional way, you see that, for instance, that under minor moderate condition, you have the displacement of this cusp signature towards lower latitude. This means that the auroral oval moved toward lower latitude, and you have a very messy situation where the storm is severe. And of course, there are no formation of small-scale irregularities under quiet condition. They actually form. The large scale, the medium scale form during quiet times, and they tend to, however, to concentrate in the midnight sector because, again, to the instabilities. Last slide. What about mid-latitudes? Are we safe from irregularities? Generally, yes, but there could be some spillover of irregularity from both high and low latitudes. This is the case of the St. Patrick Day storm. I already showed this yesterday. That the plasma bubble also formed because of the response to the storm. They formed also in the southern European sector, and we are almost submitting a paper characterizing, this is Italy, this is north of Africa, characterizing the signature of plasma bubble in the northern African, southern Mediterranean sector that affect critical operation based on GNSS in the Mediterranean. Okay, sorry for the long talk. These are the take-home messages. So be wise in treating the phase measurements. The high latitude are characterized by the formation of irregularities because of the forcing from the geospace. Low latitude are characterized by the plasma bubble in a dramatic way. And mid-latitude must be carefully taken into account for what concerns the spillover of irregularities. Thank you.